Assalamualaikum warahmatullahi wabarakatuh. My name is Wanderdania Afrina binti Muhammad Azzuha. So today, me and my friends want to share our finding about physical and mechanical properties of empty fruit punch fiber reinforced polypropylene green composite. Our goal is to study the properties of green polymer matrix composites containing empty fruit punch fibers in several aspects such as tensile strength, flexural strength, and density of the composite panel. According to facts, Malaysia is the second largest producer of palm oil. In recent years, around thousands of tons of oil palm waste are generated in Malaysia from about 200 oil palm mills and are simply disposed of without any commercial return. As evidence, in 2015, the solid biomass waste generated in the palm oil industry in Malaysia was rated about 75.61 million tons per annum, while the palm oil mill effluent or POME waste generated amounts to 65.35 million tons per year. So for those who don't know, empty fruit punch is a kind of biomass formed during the production process of palm oil. In tropical countries such as Indonesia and Malaysia, the empty fruit bunches are waste of the oil palm industry. The waste are abundantly available and has reached a level that severely threatens the environment. So due to this, numerous studies have been conducted to implement the usage of oil palm waste. With that, me and my friends have decided to make fiber reinforced polymer composite panel. So before that, I'm gonna explain to you guys about the fiber reinforced polymer composite first. So, fiber reinforced polymer composite or FRPC is a polymer that is reinforced with fiber. FRPC is high in strength, non-corrosive, and light in weight. FRPC can be divided into two main components, which is fiber as filler material and matrix as base material. In our study, the empty fruit punch was chosen as our main focus because, like I said earlier, it is one of the most abundant oil palm waste. The FP fiber also has a good potential as the reinforcement in composite. Thus, it is used as a reinforcement in our fiber reinforced polymer composite panel. On the other hand, base material, which is matrix, can be defined as the binder of a material which holds the filler material, which is fiber in structures. In our study, we have used polypropylene pellet as our matrix. Apart from that, I will explain to you about polypropylene. Polypropylene is a thermoplastic polymer widely used as an addition polymer made from the combination of propylene monomers. So the thermoplastic material can be softened through heating and processed using various methods such as injection molding, thermoforming, and blow molding. Polypropylene is often referred to as a promising plastic considering its high chemical resistance, fatigue resistant, low moisture absorption and insulation, making it ideal to be used as a material for various appliances in daily life. So these properties of polypropylene also made it a widely used matrix in the manufacturing of bio-based composite. However, polypropylene is easily affected by UV degradation, thus it is unsuitable for use in high places or altitudes where the UV penetration is high. PP is also weak to high temperature, where its performance values decreases after reaching 82.2 degrees Celsius. Subsequently, I will explain to you about empty fruit punch fiber. So, empty fruit punch fiber is brown in color, rough in texture, and medium long and thin fiber, as you can see in the picture. So it is usually dried to a moisture content of less than 8% on a wet basis before proceeding to another process besides being biodegradable and environmentally friendly. The surface of EFP is also similar to coir, which is porous and rigid. Its porous structure results in better interlocking with matrix resin. So unfortunately, natural fibers also have their weakness and problems. For instance, the structure of natural fiber consists of cellulose, lignin, pectin, and waxy substances, increasing the moisture absorption from the surroundings due to its hydrophilic nature. So this consequently causes a weak binding between fiber and polymer. So due to this, modifications of the natural fiber are made through surface treatment to increase the roughness of the fiber surface, besides reducing the moisture absorption of the fiber. So fortunately, the weakness of the empty fruit punch fiber, which is its high water absorption rate, can be partially overcome by applying the alkaline treatment to the fiber. So Alkaline treatment can be defined as the process of subjecting a vegetable fiber to the action of a fairly concentrated aqueous solution of a strong base to produce great spinning with resulting changes in the fine structure, dimension, morphology, and mechanical properties. Sodium hydroxide is the most commonly used chemical for bleaching or cleaning the surface of plant fibers, and it also changes the fine structure of native cellulose 1 to cellulose 3 with depolymerization and improve the adhesion of polymer with the fiber. So the basic fiber properties such as strength and elongation at break can be changed by a suitable choice of mercerization parameters. Mercerization is one of the chemical treatments of natural fibers most commonly used to reinforce thermoplastic. The important modification resulting from alkaline treatment in the disruption of hydrogen bonding in the negative structure, thereby increasing surface roughness. So this treatment removes a certain amount of lignin, wax, and oils covering the external surface of the fiber cell wall, depolymerizes cellulose, and exposes the short-length crystallite. So the addition of aqueous sodium hydroxide to natural fiber promotes the ionization of the hydroxide group to the alkoxide. So, why alkaline treatment is important in our studies? It is because natural fiber and polymer composites are made up of natural fibers as the reinforcing material and polymers as the matrix. So interestingly, natural fibers and polymers are usually not compatible with each other due to the hydrophilic nature of the natural fibers and the hydrophobic nature of the polymer. So this combination, like I said earlier, causes a weak fiber matrix bond. So therefore, in order to improve the compatibility between the natural fiber and the polymer matrix, the natural fiber is immersed in an alkaline solution such as sodium hydroxide for a specific time duration at a specific temperature. So it has been noted that the immersion of the natural fibers in an alkaline solution improves the compatibility at the fiber matrix interface and reduces the degradability of the resultant polymer composites. So to sum up, a lot of research has been done in the last decade, and it is proven that FRPC with the usage of treated EFP and polypropylene as the matrix can be used in various industries.
Now we will go through chapter 3, which is methodology. First of all, we have research procedure. There were 4 steps that were taken for us to produce the finishing product, that is the empty fruit bunch fiber reinforced polypropylene composite panel. The first step was to obtain the EFP fiber. We obtained our empty fruit bunch fiber from a supplier from the Malaysian palm oil board in Bangi. And next, we applied alkaline treatment on the EFP fiber. This was done to increase the surface roughness of the fiber and to reduce its hydrophilic nature, since most natural fibers are hydrophilic. We immersed the EFP fiber in 1 liter of 0.75 mol per dm cubic of natrium hydroxide solution for 24 hours. Then, the EFP fiber was taken out, hand washed with distilled water, and air dried. The next step was to produce the fiber reinforced polymer composite. I will explain more about this in the next few slides. And after we obtain the finishing product, which is the fiber reinforced polymer composite panel, we carry out a few tests to investigate and study its physical and mechanical properties. The tests that were carried out was flexural strength test, tensile strength test, structure to observe the structure of fiber reinforced polymer composite, and lastly, to study its density. So for our project, we used 4 materials to produce our composite panel, which were 50 grams of empty fruit bunch fiber, 300 grams of polypropylene pellet, 1.5 grams of stearic acid, and 2.75 grams of polyethylene. Now I will explain the procedures that were taken to produce our final composite. There were 4 steps that were carried out. First of all, we produced the polypropylene panel composite, and then we layered the polypropylene panel with empty fruit bunch fiber, which act as the strengthening material in our composite panel. In the third step, we crushed the empty fruit bunch fiber reinforced composite. And lastly, we compressed the overall empty fruit bunch fiber reinforced polypropylene composite in order to produce our final composite panel. Now I will explain the procedures that were carried out to produce our final composite panel. Overall, there were 4 steps, which were to produce the polypropylene panel. And secondly, we layered the polypropylene panel with empty fruit bunch fiber, which act as the strengthening material. The third step, we crushed the empty fruit bunch fiber reinforced polypropylene composite panel. And lastly, we compressed the empty fruit bunch fiber reinforced polypropylene composite panel. And that's how we obtain our final composite panel. And now I will explain each of the steps with details. The first step was to produce the polypropylene panel. For this step, we used the hot hydraulic compressor machine from University Technical Malaysia, Malacca. And we used 250 grams of polypropylene pellet to produce a polypropylene panel. The polypropylene pellet was placed into a steel mold with a cavity of 30 cm times 30 cm times 0.5 cm. And then we preheated it using the hot hydraulic compressor for 10 minutes. And in order to avoid the polypropylene from being stuck into the steel mold, we layered it with a plastic sheet. And after the preheating process was done, we compressed the polypropylene using the same hydraulic hot compressor machine under the pressure of 150 kg force per square centimeter for about 10 minutes. And the temperature was 170 degrees Celsius. And lastly, the polypropylene was cooled down using the same machine, but we used the lower part of the hydraulic compressor to cool it down for about 10 minutes. The second step is to layer the polypropylene panel with the empty fruit bunch fiber. For this step, we use 50 grams of empty fruit bunch fiber, 50 grams of polypropylene pellet, and 50 grams of polyethylene in the form of plastic bags. As seen in the picture, the pink color in the picture is the polyethylene. We add the polyethylene in order to add the coloring to the composite and to increase the flow of the melt. So the mixture of the said materials, which is 50 grams of polyethylene, 50 grams of polypropylene pellet, and also 50 grams of empty fruit bunch fiber, was placed between 2 polypropylene panels that were produced in this first step. And so it was preheated using a hydraulic hot compressor machine for about 50 minutes to ensure that all the heat was spread equally. After 50 minutes, the mixture was again compressed using the same machine under the pressure of 150 kg force per square centimeter at 170 degrees Celsius for 20 minutes. And lastly, it was left for cooling using hydraulic compressor machine for 15 minutes. The pictures on the left is the composite panel of all the materials combined, which is EFB, polypropylene, and polyethylene. As we can see, the PE indeed add the color to the composite panel. Okay, so the third step is to crush the empty fruit bunch fiber reinforced composite, which we produced in the steps before. So for this step, we use a crusher machine as shown in the picture on the right. So the composite that was cooled before was put into the crusher machine to be crushed. And this step was done to ensure that all the materials, which is empty fruit bunch fiber, polypropylene, and polyethylene, were mixed homogeneously. And last but not least, the process of compressing the empty fruit bunch fiber reinforced polypropylene composite. So the picture on the upper right shows the composite that were crushed. Firstly, we put the crushed composite in the steel mold that have the sample size for the tensile strength and also the flexural strength test that will be carried out after we obtain the final composite panel. After that, the composite in the cavity mold will be preheated using the hydraulic hot press machine for about 15 minutes. This step was done to ensure that all the heat was spread thoroughly through the crushed composite. And last step, we compress the empty flange fiber-reinforced polypropylene composite. Firstly, we put the crushed composite into a steel mold with a cavity of the sample size of the flexural strength test and also the tensile strength test that we will carry out after we obtain the finishing product. And then the crushed composite in the steel mold will be preheated using the hot hydraulic compressor machine for about 15 minutes to ensure that this heat was spread throughout the crushed composite equally. And then we compressed the crushed composite again after it was preheated using the hydraulic hot press machine under the pressure of 150 kg force per square centimeter at 180 degrees Celsius for 20 minutes. And then we placed two plastic sheets with high temperature between the steel mold that contained the crushed composite to ensure that the material of the composite did not stick to the steel mold when it was hot compressed. The picture on the right shows the arrangement of the layering of the compression. As you can see, the plastic sheet was put in between the crushed composite to ensure that the composite does not stick to the mold when it was hot compressed. And after we hot compress it for 20 minutes, we cool it down using the lower part of the hydraulic hot compressor machine. And that's how we obtain our final composite panel. Next, we carry out 4 tests to study the physical and mechanical properties of our composite panel. The tests that were carried out were flexural strength tests, tensile strength tests, density tests, and we observed the surface structure of our composite panel. The first test that was conducted was flexural strength test. So what exactly is flexural strength? It is defined as the ability of composite or material to resist bending deflection when energy is applied to their structure. So in our case, we conduct the test to study the resistance of our composite panel to bending deflection when we applied force to it using the universal testing machine from the University Technical Malaysia Malacca. So we used 3 samples for this test where each sample was marked into 4 equal parts. So here are the measurements of flexural samples. As we can see, the width, thickness, and area of each sample are different, whereas the length of each sample are slightly the same. The next test we conducted was tensile strength test. Tensile strength can be defined as the maximum stress that a material can bear before breaking when it is stretched or pulled. We conducted the test on our composite panel to determine how our composite panel will perform when we apply extreme force to it. So for this test, we used universal testing machine from University Technical Malaysia Malacca, and we prepared 3 samples for this test where each sample has 2 shoulders and a gauge in between as shown in the picture on the right. So the universal testing machine will apply a load with a constant rate of 20 kilonewton per minute until failure occurred, when our sample will break when it can no longer bear the force that was applied to it. So here are the measurement of each tensile samples. As we can observe, the lengths of the samples are constant, whereas the width and thickness differ. Next, we carry out the density test. This test was carried out to investigate how the density of the components in the composite against the polypropylene as the contrast will affect the overall density of the composite. So we used the machine from the University Technical Malaysia Malacca to carry out this test. And we prepared 2 samples with different mass to conduct the test. And lastly, we observed the surface structure of our composite panel using an optical microscope. This study was conducted to examine the composite's cross-section and its surface. In this test, we measured the diameter and the length of the fiber so that we can study the dimension factor of the fiber that might affect the composite structure. And that's all for Chapter 3.
Moving on to data result. The first test that was done upon the composite was flexural strength test. The weight applied on the key point surface of the composite during the flexural test was 20 kN per minute. The average stress considered the flexural strength was 12 Newton per millimeter square, which can be as high as 13 Newton per millimeter square. The average displacement taken was 13 mm but can be higher than the value as the composite were not broken. The average strain for the measurement was 12, while the average force was 40 Newton. The composite's flexibility prevents the two halves of the composite from separating completely and breaking. The next test was tensile strength test. The tensile strength test of EFB reinforced polypropylene composite showed that the displacement of the composite decreased as much as 56% from the polypropylene. The stress decreased by up to 42%. The strain also decreased up to 54%. At the same time, the force decreased up to 35%. This is due to the hydrophilic property of natural fiber that may have taken up moisture and interfered with the adsorption effect by reducing the effect of physical bonding between the fiber surface and polypropylene. After that, density test was done. The density data in the figure revealed that density gradually gets higher with the increment of mass. The density of the composite increased as much as 7% in sample 1 and 6% in sample 2 compared to the density of polypropylene, which is 0.865 gram per cm cubic. And lastly, the structure of the composite was observed. It was observed that the fibers differ in length, such that there are big difference between the fiber dimension measuring 0.16 mm, 0.17 mm, and 0.32 mm. The variance in diameter occurred due to the uneven amount of alkaline treatment applied on the fiber surface. Moreover, the dispersion of the fibers in the composite structure is uneven, as it can be observed that some of the fibers were clustered while some others were distributed homogeneously. The partial homogeneity of fibers in a certain part of the composite structure caused agglomerations due to the adhesion of fiber particles. One of the factors causing agglomerations is the moisture content of the composite. Considering the factor, it can be concluded that fibers' moisture absorption rate was not reduced even after alkaline treatment was done on the fiber beforehand. Moving on to conclusions. There were 8 conclusions made during this study. The first one is the overall mechanical performance of FRPC composite for both tensile and flexural strength is sufficient for particular building wall panels, interior automotive parts, and etc. The ratio of EFB fiber to the polypropylene is 1/6 for properties under flexural, tensile, and density. The third one, tensile strength of the composite panel with the addition of EFB fiber, which is 50 gram, was lower than virgin polypropylene due to the agglomeration effect. The fourth one, the more efficient treated EFB fiber as the reinforcement might contribute to higher flexural and tensile strength. The fifth one, each sample shows slightly different results due to the fiber dispersion and distribution variance. The sixth one, each sample has higher density compared to the density of polypropylene. The seventh, the dimension of EFB fiber observed through an optical microscope differed from one another because of uneven absorbed alkaline treatment on each fiber. The last one, the result indicated that each sample's length, width, and thickness affect the result of each test. Some of the contributions were the amount of all palm waste generated, specifically EFB fiber, can be reduced by applying its usage for industrial purpose. The next one, the potential of EFB fiber as a sustainable manufacturing material can be explored according to the specific requirements. And the last one, the possible of biodegradability of the empty fruit bunch and polypropylene composite compared to the virgin polypropylene. Hence, this concludes the presentation today. Thank you.